I'm going to talk about the impact response of 2D bistable lattices. So first of all, let's talk about what is a bistable element. Bistable element has a non-monotonous force-strain relation because of the non-convex potential that you see over here. Right? This is the potential, this is a non-monotonous force-strain relation. Therefore, we have two stable equilibrium configuration for the same force, or in other words, we have two phases with positive stiffness, phase 1 and phase 2, separated by a negative stiffness with a spinodal region. Before we move on, I want to show you a useful approximation what we use to gain analytical insight and to simplify our analysis. The trilinear approximation that preserves the essence of the bistable behavior and simplify our analysis, like I said. So we can choose 5 independent parameters to define this trilinear approximation. We chose the critical forces and the stiffnesses of the phases. Next, I want to talk about a multistable structure. Those are examples from multistable structure in our group that we have studied, the quasi-static behavior of 1D bistable lattices and the behavior of single element as well. Multistable metamaterial, we have the unique mechanical properties such as shock absorption, mechanical protection, large reversible deformation, the ability to retain variety geometrical configuration after the load has been removed, even foldable structure, and those are examples, small examples for that. But still, there are still open challenges in the 2D and 3D array that have almost never been studied, and even the dynamic response of 1D is still in its infancy. Okay, so before we move on, the dynamic response of 2D array is extremely complicated and rich, so it's instructive to use relevant insight from the 1D array. So this is the impact response of 1D array. So we found 2 different phenomena for 2 different type of elements. The first element is the stiffening element, which the stiffness of phase 2 is stiffer than phase 1, and the other phenomena that we will show next came from the fact that there is a softening element that should working. Softening element that the stiffness of phase 2 is softer than phase 1. So we have 2 different elements that give us 2 different phenomena. So let's start with the stiffening element. What you can see over here is every line over here is the elongation of a spring by time, and you can see that the impact can travel along the lattice until the wall and go back on the same shape. The wave of the impact stays the same from spring to spring and doesn't changes its shape. We call that a solitary wave. This is the analytical solution for solitary wave that I'll show you next. This is another look on the impact response. The black line is phase 1, the green is the spinodal region, and the blue line is the phase 2. So you can see that the impact moves from one spring to another. Every spring goes from phase 1 to phase 2 to the spinodal region and back to phase 1. So again, this is the definition of solitary wave. The same shape runs through the media without changing its shape. Now I want to talk about a softening element, and as you can see, it has a entirely different behavior. The energy cannot penetrate more than few masses of the lattice. So this is a great way to mitigate energy. Another interesting phenomena in the softening element is the boomerang. Boomerang like you can see over here. Again, the displacement of the spring, and this is in time, that the impact goes deep into the lattice and then go back to the beginning almost entirely. You can see the energy over here. Energy almost stay in the packet like you see over here in this packet. This is like a boomerang. This is a phenomenon called boomerang. Energy goes deep into the lattice and go back to the start. So another phenomenon that happened in the softening element on specific parameters, not in every parameters, but also in softening element. Okay, so the important insight that we learned from the 1D response is that stiffness bistable element promote energy guidance and enable the transfer energy to a long distance. On the other hand, softening bistable element tend to prevent energy to penetrate deeper into the lattice. So let's talk about the 2D bistable lattice. So this is our lattice geometry, rectangular lattice. Rectangular lattice, this is our lattice geometry. Each rod over here is a bistable spring, and in the nodes we have the masses. Okay, this is a rectangular lattice, size M with M rows on N columns. Like I said, there's a match in each not node. Sorry for the mistake. On the nearest neighbor interaction, bistable interactions, and to preserve the essence of the bistable behavior and to avoid geometrical nonlinearity, we assume small deformation. So let's talk about the formulation. This is the finite element formulation for linear truss. Okay, Q is the displacement of the nodes, and M is the stiffness matrix, K is the M is the mass matrix, K is the stiffness matrix, and so on. We neglect dissipation in our case. This is one of the impact analysis that we are going to do next. Let's continue. This is our governing equation for nonlinear truss. So let's talk about each of those components. M is a mass matrix, like I said. Q is the acceleration of each mass. F of delta is the force, the linear force, the nonlinear force of each spring, while delta is the vector of the elongation of all of the spring. So F of delta is the force of each spring. S is a matrix that connects those forces of each spring to the nodes. So this is the S matrix. So S times F of delta gives us the forces that the springs apply on each node, like a stiffness matrix time Q. How do we find the elongation of each spring? So we need another matrix G that relates between the displacement of each node to the elongation of the springs in the truss. So this is our entire formulation. I'm going to talk about the first impact analysis that we did. In this lattice, the horizontal spring, this is a heterogeneous lattice, the horizontal springs are stiffening, so we accept that the energy goes through the rows, but all the other springs, the diagonal and the vertical spring are softening. So what we expect is that the energy would stay on the first row because this is where they impact and would not penetrate to the different layer of the lattice. And this is what we saw. This is the energy map. You can see M is the number of columns, N the number of rows, M is the number of columns, and this is the energy. And the energy stays on the first row without moving to the next rows. Just for comparison, if this lattice was linear lattice with linear springs, this is what would happen. The energy dispersed through the lattice to the entire layers of the lattice. Okay. Our next analysis, our next simulation, is straight impact on all of the first masses, uniform impact. Again, the lattice is heterogeneous, the horizontal springs are stiffening, all the other springs are softening. So we accept that the energy would go straight, like the impact we apply on the masses, and go this way the entire lattice. So what I'm going to show you here, this is a very long lattice with 256 columns. So I divide it into 4 snapshots. Okay, so this is the first 64 columns, the other 64 columns, and so on. So you will see the frame move from one row to another. So let's start. This is the impact. And you can see that the shape changes through time. And after maybe 100 masses, we can see that the impact starts to be diagonal and stay like that to the entire lattice until the end. But again, this is not a solitary wave in our case. So after we saw that, we thought to ourselves, maybe we can try to apply diagonal impact and maybe get a solitary wave. This is what we did. And it stays the same, the entire lattice. The energy, maybe there is a little bit energy on the start of the lattice, but the energy stays on the same shape, the same height, the entire lattice. You want to see until the end? Okay, it goes like that with the entire lattice. To validate ourselves, we check even longer lattice with 500 columns, and we check the wave, the elongation of each spring, and we check the shape of the wave of spring number 20 and spring number 400 in the first row, and it was exactly the same shape also in the 5th row and the last row, and even in different rows for the same spring in different rows we got the same shape. So we can say safely that we got a solitary wave in these 2D bistable lattices with a diagonal shape. Let's try to see if this is work also analytically. So this is our lattice. This is our impact. So let's start. This is a Hamiltonian, the energy. Okay, so this is our kinetic energy, energy of the horizontal roads, energy of the vertical roads, and energy of the diagonal roads. So we are looking for the solution in the form of diagonal impact only on the horizontal. Okay, so when the impact is only horizontal, that eliminates immediately the vertical interactions. Now let's plug in the diagonal impact, which Qij equal to Qi plus 1, J plus 1. And that eliminates, that's exactly the same expression over here, and that eliminates the diagonal rods. So we stay only with the horizontal rods in this case. So let's introduce the elongation of each horizontal spring, which is one spring minus the other one. The spring to the side, this is the elongation of each spring. And the resulting solitary wave, this is the advanced delay equation that we got after the derivative of the Hamiltonian. Those are the forces of the spring, and from here we can get the solitary wave solution. Let me just take the water, sorry. Okay, so what we got over here? First of all, rows are decoupled. We got the same solitary wave equation for every row. So actually we reduce to 1D case. And we plug in the solution of a wave. And now we can move on to the analytical solution. So this is n is the number, this is for 1D case. N is the number of the spring. V is the velocity of the wave, and tau is its normalized time. Plug it into, this is the equation that we got before. F is a force, the derivative of the potential. When we plug it in, we get this equation. Okay? After some algebraic manipulation and Taylor series and something like that, we got this formulation of our problem, while D is the derivative operator. Okay, I'm not going to go over on the entire solution because it has a lot of detail. We use Padé approximation for each phase because we cannot solve it that way with a hyperbolic sign. So we use Padé approximation 0.2, 2.0, and 2.2. Three different kinds of approximation, of Padé approximation. In this way we could solve that equation. And this is the solution. Okay, again, I'm not going to move over the entire solution, but this is our piecewise solution. This is the elongation of the spring for phase 1, this is for phase 2, and this is for the spinodal region. And this, when we are combining all of that together, this is the solution for the solitary wave. Okay, so now we want to see what happens when the entire bistable lattice is assembled from a softening element. So as we can expect that the energy, for energy mitigation, it would stay on the first few masses. And this is what happens. The energy stays on doesn't move more than the 16 mass. Okay, so let's talk about boomerang in 2D bistable lattices. So we tried a diagonal shape impact because we saw that this eliminates the vertical and the diagonal rods. In this case, we're using not a bistable element for the tension and for the compression. Until now, we used bistable element only for tension or compression, and the other side was a linear. So we're using a double bistable element, you can say 5 linear and not 3 linear approximation. Okay, and so this is, this is example for that element. And let's see what happened. I'll talk about this in a minute. The energy goes deep into the lattice, but in some point, it goes back to the origin. And this is exactly the definition of boomerang. Okay, and what you can see over here is I sum up the energy of all of the nodes in each column. And you can see here that the energy starts in the middle, goes deep into the lattice, and then go back to the origin. Okay, so now we want to find an explanation for that. So we thought about a stiffness map because the bistable element changes its stiffness every time. So maybe this is our explanation. This is our stiffness map. Gray spring or gray rod is in phase 1, represents element in phase 1. Blue is element in the spinodal region, which is negative stiffness. And red is the element in phase 2. This is our stiffness map in the same simulation that we saw before. We can see that the stiffness changes rapidly through time to gives us the boomerang behavior. So if we think about it, in order to get boomerang, we need the stiffness of the lattice to change all the time. If it was linear spring with a control system that should changes the stiffness of each spring every time, we need very complex control group. Instead of that, we can use multi-stable lattices that change its stiffness passively due to the bistable behavior. Sorry. So like I said, the multi-stable lattice changes its stiffness passively to avoid the energy goes deeper into the lattice. This is our explanation for the boomerang, very interesting insight. So the main insight, like we said before, is that the stiffening bistable elements promote energy guidance and are able to transfer energy for long distance. Softening bistable element tend to prevent large amplitude wave to be transferred or mitigate the energy. So by smart design of 2D bistable lattice, we can control the energy and prevent it from moving from other layers in the lattice, or the energy could be mitigated entirely, or we can enable to transfer energy pockets for long distance. Our vision for next is to guide the energy completely, maybe to input from one edge and to take it out from other edge, like you see over here, or even clock certain area in the lattice that wouldn't feel any energy or any impact. That's it. Thank you for listening.